Okay, wait people, now it's time for our next speaker, Hiro-san. よろしくお願いします。
Thank you. Hello, everyone. Let's get right to it. I have a lot of things to say, so I'm going to do the formalities at the end. Long time ago, in a city far away in Geneva, Switzerland, there was a scientist named Tim Berners-Lee. This is Tim, how young he is. He was working at the CERN nuclear science research institution in Switzerland, as I said, which employs thousands of researchers and runs multiple projects concurrently. Information gets lost. Berners-Lee thought that with some imagination, he can solve this problem. In this scheme, he would have documents connected to other documents with hyperlinks, and he thought that this World Wide Web of documents will help researchers keep track of the information that tends to get lost. The links are called hyperlinks, as you know, and the text documents are written in hypertext. And the protocol that he implemented originally is called Hypertext Transfer Protocol, thus HTTP. The original implementation is very simple and straightforward. And in the year 2016, you can still do this, believe it or not. So let's take a look. We're going to connect to apple.com with Telnet. If you are doing this at home, you can play along too. After the initial, the green is not very good, but it says connected to apple.com, right? After the initial TCP handshake, you're going to get this text. And then you will type get space slash. Slash is the shorthand for the root document. And when you hit return, the server will, well, presumably when apple.com is up, there will be a response. The document will start, and at the end of the document transfer, the server will disconnect. This is the original HTTP, which later became known as 0.9. This was very simple, and people started using it. And people started using it to deliver content more than just text, including images, audio files, and so on. Browsers became a thing in the early 90s, and the vendors such as Mosaic Communications later became Netscape, and Microsoft, which licensed the Mosaic software to implement their own implementation, extensions of that protocol. There was no rule really to say what HTTP was. In the end, there was HTTP 1.0 as an informal document to describe what it was to be HTTP server, or the client on the other end of the spectrum. And HTTP 1.1 became ratified as a standard in 1999. All right, so let's look at the HTTP protocol 1.1 in more detail. This will help us understand what the advantages are of HTTP 2 when we discuss it later. All right, in a typical HTTP connection, you will see on the left-hand side, there is a laptop as the client. And on the right side, I have a desktop computer as a server. I used the desktop computer as a server because there was no server emoji. So just deal with it. All right, the time goes from top to bottom, and we will have a TCP handshake, SYN act, and act. And at the end of the act from the client will make a request. Give me /index.html. The server will give it to the client. And the client realizes that with index.html, we need more stuff like style.css, and we're going to make that request. And we also require app.js, so we're going to make that request as well. Server does the thing on the cloud, and it is going to return the documents style.css and app.js. And you can do this with Telnet as well. Here, after the initial handshake, we are going to request the document with /, and this time I'm going to say HTTP/1.1, indicating the version of the protocol that we need. And we're going to append HTTP header. Here we say host colon space www.apple.com, followed by, oops, what did I do? Followed by two pairs, right. Followed by two pairs of carriage return line feed. Upon the second pair, the server will respond with the status code, HTTP/1.1 with 200, which is the status, and the brief message, OK. And a series of HTTP headers, followed by two pairs, again, of carriage return and line feed, and the document content follows. If you're following this along at home, you will notice that the connection is not closed. Okay? If you want, you can make another request for further documents if you want. And this is basically how the web browsers will work. All right, what are the characteristics of HTTP? First, it is transmitted with all plain text headers. Okay? It is very easy for humans to understand, but it is very wasteful in terms of bytes for the computers. It is the protocol, so you can't do much about that. Second, TCP connections are kept alive. This saves the subsequent requests of making another TCP round trip for handshake, and that will add to the latency. Oops. And one of the weaknesses of HTTP is that requests are queued on the server in the order received. What this means is that if your requests are in bad order, you can have an application that is very, very slow to draw. Right? Meaning, if the first request is slow for whatever reason, the subsequent request must wait in the memory on the server before it can be fed back to the client. Think about this for a minute, and this is going to be very important in HTTP2. This is fourth one, I think. Session data are transmitted on each request. HTTP is a stateless protocol, and this is very clear from the original implementation, right? There was only one document to request. The client will ask the server of just one document, and the server will return that document, and connection will be closed. The end. Applications got smarter and smarter, and it wanted to do more, and state became very, very important, but HTTP protocol did not allow it. So you get around this problem with cookies and session headers and things like that. And there's one more, namely that browsers impose limit on the number of connections per host. The number varies between browser to browser, and it is usually 6 to 10, depending on the version and the browser you're using. This could be a bottleneck if you have to request many resources and images and things like that. And one common practice is to use domain sharding, which is to spread the assets across multiple IP addresses so that they can be served a lot more concurrently in terms of bandwidth. All right, so let's look at HTTP2. How does it differ from HTTP? As you can imagine, HTTP2 is a little too long for me. So I'm going to just say H2 going forward. So when I say H2, you're going to make an instant translation between that and that text. All right, H2 started out as an experimental protocol called Speedy at Google in 2009. It turned out to be a very fast protocol, and other stakeholders in the industry got on board, and it became the starting point for the new version of HTTP. And it was published last year as the RFC 7540 in May. All right, let's take a look at the typical H2 session. We have the same kind of diagram on the board. And let's take a look. After the initial TCP handshake, we're going to initiate TLS handshake. Boom, 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 boom. There are 2 round trips. And after that successful negotiation, we're going to start sending application data. With H2, what happens is that during the TLS handshake, there is an extra piece of information from the client in the form of ALPN, which stands for Application Layer Protocol Negotiation. Basically, the client asks the server whether or not we can use H2. This is an extension of TLS, and this is one of the reasons that often the servers and clients will require TLS to support H2. Okay. So how does that compare with HTTP? First, the headers are binary. It is very difficult for humans to understand, but it's just fine for the computer, right? And it will save some bytes transferred. There is also a companion RFC to H2 RFC called HPAC that defines how to compress headers. All right, this RFC is 7541. And very importantly, we have a connection that is fully duplex, and there are many of them you can use, one per server. All right. Here, you can send the request to server, and the server will return the request with response in any order possible. If the stream are available for the data requested, the server can push bytes as many and often as it wants. And H2 also allows server pushes, meaning that server can decide to push assets ahead of time, even if the client doesn't request it. If it turns out that the client wanted it, it will save you time, of course, but the client can still reject it for whatever reason. So it may not work the way you might think. Okay, so that was the protocol. Let's look at the H2 tooling at hand. As I mentioned before, the browsers support H2 already. Google Chrome, Firefox, Safari, Internet Explorer, as well as most mobile browsers. The red one that you see there is Opera Mini. That doesn't quite support it yet. And all of these browsers will require TLS in order to use H2 for the reasons that I mentioned earlier. And on Chrome, you can use this special internal URL-like scheme to look at the H2 connections that your browser window, I think, is using. You can look at that later. But all of these are GUI concerns, but I want something more text-oriented so that I can script things. So my favorite HTTP client is curl, and it turns out that H2 support is not very common yet. And when it is not available on that OS, you have to compile from source. How do you decide or determine whether or not H2 is supported? Turns out you can just ask it with capital V. And here I'm going to use Fedora 25 as an example. After yum install curl, you will see this output. And in the features field, you see HTTP2. I added a highlight there. So you can see that this curl was compiled with H2 support. This is not the case with Ubuntu 16.04 or OS 10, 10.11. I don't think this is any different in 10.12, which is Sierra, right? So how do you configure it? When you configure the source, you add -- with NGHTTP2 flag. NGHTTP2 is the name of the C library that implements H2 protocol. And you can install that with apt-get on Ubuntu or Homebrew on OS 10. Here, OS 10's configure flag is a little longer because I want to make sure that the features that are available on the Mac's default curl is also available on my personal copy of curl. You don't have to write this down because I'm going to share the link at the end. All right, so after that, I'm going to ask curl if your HTTP2 support is available, and it is. All right, so how does that look if I try to negotiate H2 connection with Google? You notice that I switched the example from Apple to Google because Apple doesn't support it. All right, so in the middle, you will see that LPN kicks in, offering H2. The client curl is asking the server, can I use H2? And it also tells you that offering HTTP 1.1 in case H2 doesn't work. the server comes back and says, all right, server, let's see, SSL connection using, no, not that one, not that line. Next one, ALPN server accepted to use H2. The server said, yes, I can use H2, so let's do it. You can see that huge HTTP2 header data frame is written, and even if the client asks for get/HTTP 1.1, the server will return with H2 header. In this example's case, it turns out to be a redirect, and it goes somewhere else for the country-specific server, but that's another story altogether. All right, so let's look at the things that you can do for your application to have a performant web application. Some things stay the same, right? Even if the protocol changes. So what are they? What are still good ideas? First, put assets on content delivery network. As the bandwidth became more and more bandwidth. Okay, so the broadband became more and more what's the word? Prevalent. Thank you. The bandwidth is no longer the bottleneck of the web application performance. Latency is. The server is far away from the client. It's going to take longer to deliver the content. This is laws of physics, and you have to obey them. So you want to put your assets close to the client, and you can use Content Delivery Network, CDN for short, to do that. And many of the providers now support H2. Second, you should reduce DNS lookups. You don't want many different server names on your document or application, because DNS has to be performed, and the new TCP handshake has to happen, and it's going to take a while, especially if your target server is far away. All right. Don't do redirects, because it is basically a wasted request. Same way, DNS lookup has to be done, TCP handshake has to be performed, and the new request has to be handled, and this is just a bad idea. Some things change, and let's look at what are good ideas in H2. First of all, you should find out whether or not you can use it. Right? This is dependent on your applications, so I'm not going to tell too much about it. If you're on PaaS, you may not have server choices, and you may not have that choice. You want to split assets, probably. Under HTTP 1.1, it is common, to concatenate assets into a single file, so that when you make a request to that single asset file, you don't have to take too many slots on the browser's quota. With H2, you don't have to worry about that too much, because the files can be cached independently and pushed separately. If the files are too small, though, you might incur overhead more than you save. So you probably want to test a little bit. And you don't want to shard domains, because you don't have to. Fully duplex, multiple connections will let you take care of that. And finally, you want to test different servers. because H2 implementations vary from server to server, and some features that you want in your application may perform better on one server to another. All right, so we talked about the server in general, but there is a question about, what about Ruby? All right, so let's look at the Ruby server code. The server code, I have some not so great news. When we talk about HTTP server on Ruby, it is either Rails or Sinatra. There are other things, I think, but that's probably minority, I think. And Rails and Sinatra depend on rack, and rack is very simple and is very easy to understand. The server object gets a environment object, and it is going to return a triple of HTTP status, hash of HTTP headers, and a response object that responds to each. Remember, H2 is a fully stream protocol, and Rack's default is to have this response object ready when the client makes a request. This is not going to fly very well, and it needs a lot of work to have Rack work with H2 well. It turns out, though, you can hack this protocol, and you can use the API to do that. And I think there is a session on this very subject next upstairs. Is that right? I think. Okay. Aaron Patterson worked on getting Rack and Rails on H2 a little over a year ago, and as far as I know, this has not been merged to the master yet, so it's going to be a little while before any of these things are going to be available to you and your application. But maybe it's not that important because many of the HTTP servers will allow you to proxy things, and you can just set up the H2 server on front and accept H2 connections from this client and just proxy everything to the Ruby application servers on the back end. Maybe this is enough to get you all the performance boost you need. Maybe. What about client? Client, things are a little easier because there are two. Can you read it? The links are going to be shared at the end, so don't worry too much. There are two implementations, one called HTTP-2 by Ilya Grigorik, which is pure Ruby implementation, and the other one is called DS9, which is a wrapper around NG HTTP2 library by Aaron Patterson. These libraries do not downgrade to HTTP 1.1 when H2 is not available. So if you want to write a robust client software, you're going to have to do a little more work than just that. All right, I'm running out of time. And let's recap. All right, we have discussed the history and details of HTTP 1.1 and H2. H2 addresses many shortcomings of HTTP 2, by playing to the strengths of H2, you can start planning for the future upgrade to H2 now. While we are still sorting out the best practices, if your deployment environment allows it, it is definitely worth starting playing with it today. All right. Thank you very much. This is the link that has everything that I have shared on this talk. On GitHub, I think I'm gonna keep this up for a while. I have stickers.
Any questions?
Oh, please. So if you want the stickers, just come see me. Thank you, and I'm ready for questions.
Okay, the gentleman at the back. You want stickers? Very cute stickers.
I have many.
Hello, thanks for the talk. And I was wondering, has Travis put H2 into production, and how does it affect the entire performance of Travis itself?
Okay, thank you for the question. We have not done it because we are on Heroku, and Heroku by default does not support H2 yet. Heroku's web server is called Cowboy Coup, I think. And from what I understand, there was some problem. Can I say that? Oh.
And the second question is that, can we use another, for example, web server like Nginx or Apache to translate H2 requests into HTTP 1.1 and push and transfer it to RAG for processing?
So I think that is also available. I think there is a binary in the ng HTTP2 suite that will do that. But I think we can just use proxy instead of the translation. I haven't tested the translation from H2 to HTTP, so I don't know how well it works.
Okay, thank you.
Okay. John, you have a question?
Might have been answered. I'm not sure. Sure, I'll try. Why not?
Oh, sorry, hijacked. Sorry.
I guess I'll just stand up and talk loud. So I have two questions. One, it wasn't clear from the slides. Do you have stickers?
The question was, do I have stickers? And yes, I do.
And the legitimate question is, when you're using a proxy to do the conversion between H2 and H1, what sort of performance implications does that have? I'm not sure if that's if you have an answer for that, so I'm just kind of curious.
The question was, when you do proxying, is there any performance penalty?
Yeah, or what is the penalty? Because there will be.
Okay. All right. So I think there. Okay. So I have not run any benchmarks, so I can't say for sure. But there are a few factors at play. One, between the Nginx and the application servers, there's no TLS, right? If you do the proxy over HTTP instead of H2, and there's not a whole lot of performance gain, and not gain, but performance loss, I think. From what I saw when I stood up Nginx for testing certain applications on Travis, it is generally good because Nginx can serve the assets way faster than Heroku's servers can. I can't compare those two things side by side, of course, but the my tendency, I would tend to think that having a H2 connection between the proxy and the application servers is not that critical. I think the jury is still out though. So
I'll have to do some benchmarks.
yes.
Cool. Thank you.
Okay, we have one more question and one last question.
Can I have some stick?
Yes.
That's okay.
Yes.
Can I have some stickers?
Yes.
Actually, I thank you for your sharing. Actually, I use H2 in my Rails project, and as you said, I don't Rake actually doesn't support H2 very well because they respond a bundle of the HTML or anything once. But it sounds like so I use H2 in Rails doesn't help very well, but in my experience is like work well and make my website faster. But I don't know why.
I wouldn't know either, but it's problem. It could be many of the things, right? I just don't know the details of your application. So.
Well, in that case, I think it's best that you guys can talk afterwards in more details. Well, thank you very much. Thank you, Hiro-san, for your lovely sharing.